Hello, everyone. My name is Sam Guidroz, and I am a graduate student at the Department of Construction Management at Louisiana State University's College of Engineering. Today, I'm going to be speaking about the feasibility and mechanical properties of an emerging class of engineered cementitious composite with Portland limestone cement, Class C and Class F fly ash, and sugarcane bagasse ash combinations. I would like to begin the presentation by touching on the importance of concrete in our global infrastructure. It is common knowledge that concrete is present all around us. It's in our homes, our offices, our roadways, parking lots, drainage systems, and so much more. It is estimated that the global population uses over 11 billion tons of concrete every year. Concrete is the most widely used construction material on the planet, and it's unique compared to other civil materials due to its ability to be adjusted for specific environments. For example, additives and admixtures can be included in a mix design to allow for a bridge in a higher sulfur environment to be better protected against corrosion. Concrete is also very workable, and it's able to be cast in many different shapes, such as beams and drainage pipes. While concrete is undoubtedly important, there are some shortcomings that need to be discussed. Concrete is brittle by nature and is prone to various types of cracking, particularly in roadway applications. Environmental effects and continuous loading from traffic combined with concrete's poor ductility and low tensile strength is a limitation that cannot go unnoticed. We see here that oftentimes cracking can lead to water intrusion and the corrosion of rebar inside of concrete structures. The concrete industry also draws in a lot of criticism. The production of cement accounts for approximately 8% of the global CO2 emissions. The process of converting clay, limestone, and other materials together, known as clinker, takes a great deal of energy and releases large amounts of carbon dioxide into the atmosphere. To put into perspective how much cement is utilized, in 2019 alone, 89 million tons of cement was produced. The concrete industry also uses nearly 1/10 of the planet's industrial water supply, further increasing the criticism that concrete is not beneficial to the environment and lacks sustainability. Solutions to these problems are to create a more sustainable cement industry. This can be accomplished by utilizing byproduct materials within the cement production process. The opportunities to encompass sustainable, supplementary cementitious materials within the manufacturing process of cement has already yielded promising results. One solution that has received a lot of attention in recent years is creating more sustainable mixtures of ECC. ECC, also known as engineered cementitious composites, are a class of high-performance, fiber-reinforced cementitious composite with high tensile strength and ductility. As shown in the lower right corner of your screen, ECC has been commonly referred to as bendable concrete due to its high ductility property. Fibers within the mixture increase the flexural capacity of the materials. During this particular research, polyvinyl alcohol fibers were utilized, which is at the top right of your screen. ECC was developed in the early 1990s by a team of researchers at the University of Michigan, led by Dr. Victor Lee. It was developed on the primary principle of micromechanics and belongs to a large family of fiber-reinforced concrete. Many advances have occurred since its original development to make the material more cost-effective and to improve the sustainability and practicality. The advantages of ECC are outlined by its exceptional performance against cracking. It was designed to limit the propagation of cracks, which reduces the repairs that ECC systems require compared to conventional concrete systems. ECC can also be developed utilizing supplementary cementitious materials to improve the product's sustainability. The limitations of ECC is that the materials required to develop the mixtures are expensive and not readily accessible. Manufactured microsilica sand and PVA fibers are oftentimes challenging to obtain and are expensive. ECC also requires more cement than conventional concrete mixtures due to the lack of coarse aggregates in the material, which further increases cost and CO2 emissions. High cost and low practicality compared to regular concrete have limited data in the field implementation of ECC and the ability to collect data. As shown in the figure, ECC materials showcase steady state microcrack formation characteristics rather than macro cracks that we see in conventional concrete. High tensile ductility is 100 to 800 times that of conventional concrete, while flexural strength is 2 to 3 times stronger than conventional concrete. The objectives of this study are to evaluate the mechanical properties and material performance of an ECC that is composed of more sustainable materials. 4 sustainable materials will be used as partial substitutes for the high content of cement and sand included in regular ECC mixtures. Sugarcane bagasse ash is an agricultural byproduct of sugar production and has caused significant containment problems throughout Louisiana. This material will be utilized as a partial substitute for microsilica sand. Class C and Class F fly ash is an industrial byproduct of refining coal at power plants and also presents its fair share of containment problems. Fly ash will be used as a partial replacement for cement during this process. And finally, Portland limestone cement, also referred to as Type 1L cement, will be utilized rather than Type 1 ordinary Portland cement. PLC is a more sustainable cement because it allows for a reduction in clinker, which reduces the greenhouse gases emitted during the cement production process. Each of these materials combined creates a more environmentally friendly and sustainable form of ECC. A series of 9 total mixtures, 3 control mixes of regular ECC, and 6 treatment mixes of sustainable ECC will be developed, each combining varying amounts of fly ash, SCBA, and PLC. Each mixture will occur within a planetary mixer. Dog bone samples will be utilized for tension and flexural testing, while cylindrical samples will be used to test compressive strength. Once mixed, the materials will be poured into molds where they will set for 24 hours. Then molds will be stored for 28 days in lime water to allow for adequate curing time. The picture on the right of your screen shows the lime bath the materials will be stored in. Once 28 days elapse, samples will be removed from the lime bath and the mechanical properties of each mixture will be tested and compared to the 3 control mixtures. I also wanted to emphasize the fact that all of the byproduct supplementary cementitious materials were obtained from the local Baton Rouge area, further suggesting the materials are readily available for implementation. To analyze the mechanical properties of each sustainable ECC mixture, each of the following tests will occur. Testing will include determining uniaxial tensile strength, compressive strength, flexural strength, fractional toughness, and surface resistivity. The image at the top right is an example of a compressive test, and the image at the lower right is an example of a surface resistivity test. Attached here is the design matrix for each of the 6 treatment mixes developed for the study. I want to acknowledge the Louisiana Department of Transportation and Development's Materials Testing Lab and the Louisiana Transportation Research Center's Concrete Lab. All of the mixing and material testing that occurs throughout this project will take place at these facilities. The expected outcome of the research is that an ECC that is more sustainable will be produced while yielding the same promising material properties and characteristics as conventional ECC. I also expect that mixes with higher amounts of SCBA will show improvements in surface resistivity and tensile strain capacity, while mixes with higher amounts of fly ash will reduce crack widths. These were characteristics that were identified in previous studies. Overall, the goal is to develop a more sustainable class of ECC that meets the established performance criteria. As I touched on in the beginning of the presentation, sustainable ECC, like regular ECC, can be implemented on various types of civil infrastructure systems. This material is expected to reduce emissions created during the cement production process and use materials with little economic value. All of this will be done while introducing a smarter way of improving the deteriorating infrastructure of our planet. Sustainable ECC is more cost-effective over time and can be produced right here in our backyard from materials that have little use or economic value. As a relatively new construction material, ECC's future must be focused on sustainability and improving the future of the industry as a whole. With this, I will be concluding my presentation. I will be glad to answer any questions about the research. Thank you all for your time.